Hello all. In this video series, we will be looking at buffer overflow attacks. Before you actually start with this video series, I would strongly encourage you to look at the assembly language primer video tutorials which I have already created and are hosted on SecurityTube. The reason being that to get an in-depth understanding of buffer overflow attacks, we will really need to get our hands dirty with assembly language code. Well, that's all the prerequisite that is required for this series. So let's begin. So in this part 1, we will be looking at how to smash the stack with a buffer overflow. So exactly what is a buffer? Now, very simple definition. A buffer is a temporary space in memory which is used to hold data. And a buffer overflow happens when data written to a buffer is generally larger than the size of the buffer itself. And due to insufficient bound checking, there is an overflow and adjacent memory locations are also overwritten due to this large amount of copying which is happening. So now let's understand buffer overflows in a slightly more in-depth manner. Now let's take a sample vulnerable function called getInput, where we have defined a character buffer of size 8 bytes. Then we go ahead, use the gets function to go ahead and get user input to fill this buffer up with a string. And then we go ahead and once again print the string onto std out. So exactly what is the vulnerable code here? Now, if you look at it, the gets function itself is very dangerous, simply because it does not check the size of the buffer variable into which it needs to write the user supplied data. So hence, if let's say the user supplies more than 8 bytes of data, then gets will still happily go ahead and write that onto memory, even though it actually overflows the size of the buffer variable, right? So the important thing to note here is that gets itself does not check the input size, and in many cases it could be greater than the size of the buffer, which will result in an overwriting of adjacent memory locations. Now, why is this a security vulnerability? Now, in order to understand that, we need to remember the stack layout. Now, we've discussed this layout in detail in the assembly language primer video series. So if this is not familiar, please revisit that video to look at exactly how the stack looks like. But very briefly, stack actually grows from high memory to low memory. And whenever a function call happens, the arguments to the function are first stored onto the stack. Then the return address is stored, which is actually the next instruction the processor has to execute once it returns from that function. Then the EBP value, the old EBP value is actually stored onto the stack. And then the local variables which are defined in that new function are once again stored on the stack. So now let's actually go ahead and look at the sample program we discussed in the last slide to understand this in a more in-depth fashion. So created a sample program demo.c. Now all this program does is defines the getInput vulnerable function, which we've already discussed, and in the main function just calls getInput. Right, so let's quit and compile this function. So if you notice, we've given the -GDB option so that a lot of more information which GDB can actually use later on to help us debug the program will be embedded into the final executable. Also, we go ahead and say that the preferred stack boundary is of size 4 bytes. Now, you see a 2 here, but what this means is 2 to the power of whatever you mention here. So this is nothing but 2 square, which is 4 bytes. We'll discuss the preferred stack boundary in later videos in more detail. So right now you need not get too concerned about that. Let's compile the program. And if you notice, we get a warning from GCC telling us that gets is actually a dangerous function. The reason of which we've already discussed is that it does not go ahead and check the bound of the input with respect to the buffer into which it is writing. Anyway, so the program has compiled, and now let's run the program. So it is waiting for our input. Let's say I given Vivek, and as expected, it prints out Vivek to std out and exits. Let's see what happens if we go ahead and increase the input size, right? So let's say, hello, Vivek. Right now it is around 12 bytes which we've inputted. Let's go ahead and input the size more. Hello, Vivek R. If you notice, right now the program has not exited, but it is waiting. If I press another input, go ahead and get a segmentation fault. Now if I go ahead and increase the input further, we immediately get a segmentation fault, right? So exactly what is this and why is this happening? So let's go back to our slides now. Go to the next slide, and now let's try and understand the stack layout of our vulnerable program. So if you notice, if you go back to the program code very quickly, the getInput function does not take in any arguments. Thus, there are no arguments which will be pushed onto the stack. However, when the main program goes ahead and transfers control to getInput, it will go ahead and push the next instruction address, which would be return 0, onto the stack. Then once the execution goes into getInput, the old value of EBP will be stored, and then the local variables will be pushed onto the stacks, in this case buffer 8, right, which is 8 bytes as expected. So if you look at it, actually small mistake, the ESP would actually be pointing here, the top of the stack, and basically there are 8 bytes of local variable, which is nothing but the buffer variable. Then we have 4 bytes onto the stack, which is the old value of EBP which has been stored, and then we have the return address, right? So now let's go ahead and verify this in the program itself. So let's actually quit the program again, load the program into GDB this time, list the program. So let's actually place 2 breakpoints. Actually, let's first place a single breakpoint at this position, which is line number 13. And let's then place another breakpoint at line number 7. Now let's go ahead and run the program. Actually, before that, let's go ahead. If you remember from the assembly language primer, we can disassemble the main routine, and we can also disassemble the getInput routine, right? This is the code. So if you actually look at it in the main program, we are calling the getInput function. After that, as expected, we are moving the value 0 into EAX, which is the return value, and then going ahead and exiting. Here in the getInput function, we first push in EBP as expected, and then we go ahead and move the current value of ESP into EBP. All of this has been discussed in detail in the assembly language primer, the whole function beginning and what happens and all of that. So have a look at there. And then finally, space for the local variables is reserved. So if you remember, the size of the buffer, character buffer, is basically 8 bytes. That is the character array. And exactly that much is reserved onto the stack. Then from there on, I guess, we go ahead, do the gets, then do the puts, etc., etc. Okay, so with this in place, now let's go ahead and run the program. So we've hit the breakpoint at get input. Now let's go ahead and look at the stack for the time. Let's print, let's say 8 words in hex on the stack. So we notice before the get input function is called, this is how the stack looks like, right? This is what the top of the stack is pointing to right now. Now let's go ahead and step through this function, the code. So now we are already into the get input function, right? If we look at the stack right now, what we will notice is that the different places on the stack have now the addition of the return value as well as EBP. So let's actually look at how all that has come together. So the top of the stack first was actually going ahead and pointing to this data. If you notice right now, this is where this data is. And there have been 16 bytes on top of the stack which have been actually pushed onto the stack. Now, where are these 16 bytes coming from? Right? If you go back to our image, you'll actually notice that the first 8 bytes is actually nothing but the local variable buffer. The next 8 bytes is nothing but the value of EBP. And the final, the next 4 bytes is nothing but the value of EBP. And the final 4 bytes is nothing but the return value where execution should continue after returning from this function. Now let's go back to the code, and what you will notice is that hence these 8 bytes are nothing but the buffer variable. This is nothing but the old value of EBP which has been stored onto the stack, and this is the return value. You can verify this by going ahead and looking at the code which is there at this memory location. So let's disassemble the code in this memory location. And if you notice, this is nothing but the next instruction, move 0 into EAX after the call get input function returns, right? So I guess if you understood everything correctly till now, then practically you got most of how buffer overflows are going to work. If you haven't understood till here, so now let's look at what else we can do at this point. So we are inside the function where we go ahead and the gets buffer routine is going to be called, right? So let's actually step through this instruction so that we are asked for the input. So we are being asked for an input right now. Let's go ahead and add a large value, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F, right? Let's give that input. If you notice now, well, things are fine. However, let's actually print ESP right now. So if you notice, what has happened is that the top of the stack was here, right, at this memory location, which is exactly where it is even right now. However, if you notice, our return address has been mercilessly overwritten by the input we just provided. And if you notice, 64, 65, 66, these are nothing but the consecutives ASCII values of some of the characters which we've inputted here. So the return address has been overwritten, right? However, execution still continues in the same function, because right now the function execution part has not really been corrupted. So let's actually step through this. So the same output has been printed out, right? If you notice, this is actually the trailing null of the input string. Now let's try and go ahead and step further. So if you notice, we receive the segmentation fault, and it actually says, hey, where is this? I mean, this does not correspond to any place I can execute in the program, right? This is the value of EIP right now, right? This is the value of EIP. This is exactly what we overwrote with our input. So if you notice, this is how using a larger input than what a given buffer can take, but still forcing a copy, we are able to overwrite the return value which is stored onto the stack. Let's go back to our slide. So basically, what are our various observations, right? In order to go ahead and fill the return value, we need to, in this program, cover the first 12 bytes, right? 8 bytes of the buffer variable and then 4 bytes of the EBP variable. Once that is done, the next 4 bytes is what is going to dictate the new value of EIP, right? And if the input is large enough, it is going to override this return value. And once the function execution is actually over and this return value is popped off the stack, whatever we insert here is going to decide what is going to execute next. Now, in the previous example, we went ahead and actually put in a garbage value which did not correspond to any executable instruction which is there in the program memory. And thus, basically, we got a segmentation fault, right? So now let's go back and see if we can override the value of EIP with our input with something where we can go ahead and do something interesting. So let's exit GDB and let's make a quick modification to our program. Let's add a new function, can never execute. Right. If you notice, can never execute is not called by any of the other functions in turn. Thus, it can really never execute during normal function calls. Now let's go ahead and compile this program again. We get the familiar gets warning. Now let's go ahead and run the program. So we can give a large amount of input, and of course we get a segmentation fault as desired. Now, another way to give input to a program is by also using the printf program. So let's say you want to give a large input, we can go ahead, say printf blah blah blah, and then pipe it, into the program. So if you notice, the input was given, this is the output which the program gives us, and of course, as expected, there is a segmentation fault. Now, the interesting part of the printf program, if you look at the man page, is that you can go ahead and actually insert bytes just by using their hexadecimal value. Now, this is important because generally many of the bytes which you might want to input might not really be printable characters, because of which we cannot really type them in using a keyboard. Now this is where we can actually give the /x switch and then go ahead and give the appropriate hexadecimal value for the byte which you want to input. So as an example, let's say if this is the value we want to input. So what we've done is a couple of capital A's here, and then we are inputting a character which has a hex value AA, and then another character same with hex value AA. So if you notice, this has now been inputted into the program. Okay, so what we need to do is, if you load up the program in GDB, and let's say we go ahead and list the program. So what we want is somehow if we can execute the can never execute program, right? So how do we do that? Let's disassemble this first. Can never execute, and actually look at where it is. So this is actually the memory location where can never execute is actually present, right? So the return value which we need to overwrite on the stack needs to be filled with this specific value. If this is the return value, then once the function returns, the next instruction will be the first instruction in can never execute, which will be executed. So let's exit the program, go back to our slide and see how we can engineer that. So if you notice, we don't care what the first 12 bytes are, right? What we really want is after the 12th byte, the next 4 bytes need to correspond to the return value. So let's actually use the printf program, and given the first 12 bytes 1 2 3 4 5 6 7 8 9, and let's say 10 11 and 12, right? Now let's go ahead and input the return address. Now this is the next 4 bytes where we are going to return the input address. Let's feed the hex values in. Now a point to note is that we need to fill them in reverse order, right? I leave this as an exercise to you to figure out why we need to feed them in reverse order. It's a very simple thing. Just try and remember how memory is actually laid out. Right, so if you notice, we've now taken 84, then 83, then 04 and 08. Now let's go ahead and run this program again. So if you notice now, there is a segmentation fault. However, I can never execute has also been printed onto the screen, right? So this is where what we've done is, with a very specially crafted input, we were able to change the course of the program, and after it actually returned from the get input function, we were able to forcibly have it get inside the can never execute function. It printed that, and then after that returned. Now, why did the segmentation fault happen? Simple reason is because we've already corrupted the stack. There was no way for it to actually to be able to get back to the original place in the main routine where it could have exited gracefully, right? So the way in which we can make this happen is go ahead and use the exit function inside the can never execute function itself. So let's actually go ahead. So let's open up the demo.c program and actually also add an exit call here itself. Let's recompile the program, right? And then let's go ahead and again look at the return address. Okay, so this is what the return address is. Should be actually. So now let's go ahead, call the demo function with this as the new input. First we have B4, then we have 83, then we have 04, and then we have 08. And let's run it. Oops, I forgot to give the hex values for the others. Here. So now all of these will be interpreted as hex values, right? So now if you notice, the I can never execute was actually printed and the program exited gracefully, right? And the answer to that is pretty self-explanatory, is that if you actually disassemble the can never execute function, you'll actually notice that in the end there is a call to the exit system call, right? And because of this, even though the stack has been corrupted, there is no way it can return back to the main program from where it could exit. It can still go ahead and exit gracefully using the exit system call. So well, that's all for this video. What I wanted to demonstrate is by using a very simple program, it is actually possible to go ahead and change the course or the flow of the program by using a buffer overflow attack. Now in the next future videos, we will go ahead and look at how to exploit such a buffer overflow situation. I would really love your comments on this video. So please take a couple of moments to actually give in your valuable suggestion and comments in the comment box below. And look forward to seeing you all in the next video. Thank you.